Good morning students, welcome to the first lecture, the MOOC lecture on principles of vibration control. This lecture we will cover the the whole thing in a manner that first of all the reference part that I should be telling you that you should have these principles of vibration control by A.K. Malik, affiliated by East West Press India. Is a very good textbook which we will more or less follow in most of the sections, and except from some of the advanced sections where we will go for some of the reference books in this course. For example, we will see this book Vibration with Control by Daniel Inman, and we also will see Vibration Damping, Control and Design by Da Silva. Dynamics and control of structures. This is important particularly when we will talk about active vibration control. For passive vibration control, the principles of vibration control are well actually discussed in this book by Professor A.K. Malik, but there is a, for the continuous system there is also a good book which you can use for reference, that is called Passive Vibration Control, and that is by Dennis J. Mead. And for active control again, vibration control of active structures by Andrew Fremont. Finally, there is some part of it where energy harvesting I will be discussing. So, there these piezoelectric translators for vibration control or damping by Mohirmani and Fleming's book will be important for you. So, one basic textbook we will use in this course and 6 reference books, as and when required I will mention it to you. You should try to catch hold of it from a library or from internet, and you should try to see these books or read these books. So, today is the first day in which it will be an introduction to the principles of vibration control. Now, in this lecture we will talk about what are the adverse effects of vibration, because that will give us the motivation why should we go for vibration control, and then we will try to also talk about that how can you quantify the vibration, what are the quantitative parameters that you can use for this. So, the parameters of the vibration system or a vibrating system. Then we will of course talk about that how can we control the vibration in terms of strategy. That means we will talk about various active and passive control strategies, and some of them I will try to kind of elaborate in this lecture and some in the next lecture. So, that is what is our plan in terms of spreading the lecture. So, the first important thing is that what is a vibration. In terms of, I would rather say that what is a mechanical vibration. So, that we will be considering, okay, because vibration itself is a very extensively used term for many applications, but in the context of mechanical vibration this will be some kind of a to and fro motion about some equilibrium configuration. So, whenever you will think of it, you will think of that it is as if like you have a pendulum and you have given a small displacement to the pendulum by an angle theta, and the moment you do that, the pendulum starts to move. It is a single degree of freedom system and a small angle, but it starts to move, oscillate until and unless the air finally damps the pendulum. So, this kind of a small to and fro motion. Now, of course, the motion of pendulum per se is not a vibratory motion, but it is a to and fro motion. If you in fact, and this is a very good actually symbol of vibratory motion, instead of taking the pendulum, now suppose we take something which we are more familiar with. For example, we take a plate. Okay. So, here is a plate for us, and on this plate suppose the plate is supported in the two sides, and on the central point of the plate I am applying a force so that the plate gets deformed a little bit. I am not deforming it too much, and then I release this force. So, once I do that, then the plate starts to vibrate very much like that motion, to and fro motion of that pendulum that we have seen. So, it will start to vibrate like that, up and down until and unless the damping inside the plate and the air damping etc. bring it back to a stop position. So, that is like a similarity between that what is happening to a pendulum case and what is happening to an actual case of vibration, a case of mechanical vibration which we will be considering. Now, this vibration is undesirable in all the engineering systems, because as you can see that this particular plate case, that the plate is vibrating back and forth and back and forth, and you consider that that plate is a part of an aircraft fuselage. So, what will happen is that something like a fatigue failure will happen to the system. So, if a structure is subjected to repeated tension and compression, tensile stress and compressive stress, that's how we define the fatigue loading, then or a variation of tensile stress or a variation of compressive stress, any one of these three variations let us say, then the structures, the cracks inside the structure get sufficient energy to propagate, and in the long run the structure fails, which we call as the fatigue failure. So, naturally fatigue failure is undesirable in vibration. There are also other cases. For example, you are trying to actually make a very nice small workpiece for some machine tool application, and that cutting tool starts to vibrate. Then there will be a loss of accuracy of the workpiece. I will explain it soon with the help of some slides. Similarly, there could be cases of malfunctioning of sensitive instruments or systems like a payload due to vibration in a launching rocket, or there could be severe damage due to resonance in terms of collapsing of bridges or transmission lines or offshore structures. So, all these are various ill effects of vibration. Now, it is not that vibration is always very bad, at least you know that there are some cases where vibration is very much desirable. One case you can think of readily is the case of musical instruments, because in the musical instruments once you vibrate it at a particular frequency, and if there is no noise in it, that is if your desirable condition is that it keeps on vibrating at a pure frequency level or maybe in its subharmonics or superharmonics, then the sound that gets generated from a musical instrument, that becomes very much like attractive to our hearing system. So, as a result vibration is desirable for musical instruments. Similarly, there are some other applications. For example, there are some applications of assembly where actually we use vibration in terms of the assembly system. Then you might have seen that how concrete is compacted in some of the construction sites. There the vibration is used in terms of mixing the concrete very well with the gravels. So, like that there are some cases where vibration is actually desirable, but in this particular course we will consider cases where vibration is not desirable, and hence somehow we have to control this vibration. Now, I told you that I will elaborate each one of these cases. For example, the first case, the loss of accuracy of workpiece, shifting of tool position due to vibration of cutting tool. Suppose you see that this is the thing that you have to carve, as you can see in these dotted lines, and the cutting tool is placed here. Okay. So, we are carving material out of a maybe a kind of a shaft, and this is the ideal location, but whenever there is a vibration, then the tool actually cannot be remain at this location, it is going to this particular location due to vibration. So, you can see the same thing that is happening here, that there is this workpiece here, this is the workpiece, and there is this feed direction of the tool, and there is a vibration that is happening, and as a result it is not staying at this location, but going to some other location. So, naturally if this happens, then you will not get a smooth cut, rather you will get a very zigzag kind of a cut, which is not desirable at all. So, this will happen, that means the machining will completely fail, or at least it will give you a degraded performance due to the chatter vibrations. In fact, there are two types of sub chatters that can happen. One is called a forced chatter, which originates in the driving system itself. For example, there is some problem in the motor that is driving the tool, and as a result that gets transmitted to the cutting zone. So, it is coming from the motor, that is what can be a case of forced chatter. The other case can be self-excited chatter, where the chatter is generated due to uneven surface of the workpiece, fractures of metal chips, etc. That means, the cutting tool that you have chosen is not really very proper, and instead of cutting it is undergoing lot of friction, and that is generating some kind of a self excitation in the system. So, in that case also you will get a similar degradation in terms of the performance of the system. So, you can have chatter both as a forced chatter as well as a self excited chatter, and for depending on the case to case we have to have different strategies of vibration control. I was talking about fatigue failure. Now, fatigue failure not only can happen to an aircraft structure, but can happen to even any mechanical system. For example, you can think of a diesel engine, and many a times if you look at the camshaft assembly of the diesel engine, then you can see that it is designed in such a manner, these cams and the camshafts, you can see that it actually generates a kind of a periodic excitation force. So, that periodic excitation force actually creates a periodic acceleration of the piston, the connecting rod and the crank. So, this crank is subjected to a periodic excitation force. Now, if that happens, then this kind of a system will at the end develop a fatigue, and as a result you will see this kind of a failure that has happened to the system. It not only happens due to this periodic acceleration, but also it can happen if there is a periodic variation in gas pressure inside the engine cylinder. So, fatigue failure is kind of a very common failure, which is due to what we will call the torsional oscillation. Okay. This excitation comes to these shafts in terms of torsional oscillations of the shaft. So, unlike the last case where there was this up and down to and fro motion, in this case the motion is actually in terms of torsion. That means, suppose you have a shaft like this, one end is closed, and so due to this periodic excitation it will rotate right and left, as if you are actually twisting the system, right left continuously. This kind of periodic oscillation will occur to the system, and as a result there will be a breaking of the camshaft. Now, I also told you that there are some cases where this is very important, where you do not want the vibration to get transferred to a system which you want to save, which is very sophisticated system, which is very much prone to vibration. So, one such case is actually the rocket itself. As you can see that this is a launch vehicle of the rocket, and it has an isolation system like this, and it is the spacecraft which is so expensive and so kind of a fragile system, you always want to save it. So, this isolation system is designed in such a manner that the vibration from the launch vehicle will not actually go to the spacecraft. In fact, if you just expand this, you can see it here that this isolation system, which is also known as a Stewart platform, is based on 6 actually such kind of shafts, and in each one of the shaft they actually work as a kind of a low frequency cutoff system. So, these hexapods work in such a manner that even if there is excitation from the bottom, they actually cut off this, and that table, the platform becomes free from vibration. So, this is a Stewart platform in which this system is implemented. Now, we will come to the quantitative description of vibration, because I already have shown you enough evidence that vibration is not desirable, vibration is going to create failures. The point is that in order to do something effective, I need to quantify the vibration. So, there are 3 things that are important here in any vibrating system, that is the system itself. I have shown it through this analogy, that the vibrating system itself, the excitation of the system, as you can see here, that this is the system which is undergoing an excitation due to base excitation, and the response of the system. So, once again these 3 things if you can quantify, first of all, what is the system that is vibrating, how the system is getting excited, that if we can quantify, and due to that excitation what is happening to the system, like in this case the angular amplitude you can see, that is the response. So, that actually quantifies the entire description of the vibration. Now, based on this, first thing is we have to then define the system itself, the vibrating system. There are 3 things which are used to define a vibrating system. The first one is the inertia, which is linked with the kinetic energy of the system, because there is a to and fro motion happening to the system. So, there is a kinetic energy that is actually associated with the system. Secondly, with the potential energy stored in the system, there is the stiffness that comes into picture. If we consider only inertia and stiffness, then we can say that our system is conservative system in nature, where actually the potential energy and the kinetic energy is interchanged, and in such cases the vibration will continue for indefinite point of time. But in reality that would not happen. In reality some amount of energy will be always dissipating, and that will get transformed in terms of say thermal energy, say sound energy. This is what we will be calling as the damping, that indicates the energy that gets dissipated from the system in each cycle. Now, when we will talk about inertia, we can think of inertia in the rectilinear frame. In that case inertia will be equivalent to mass, and if we think about it in the angular frame, in that case it will be equivalent to the moment of inertia. And when we will talk about stiffness, if it is in the rectilinear scale, then it can be like a linear spring, okay, in which you are applying the force and the spring gets deformed. So, that is a linear spring. However, its counterpart in terms of angular reference frame is a torsional spring. In the mechanical clocks that is used to be used in earlier days, we used to use a key in order to give the torsional energy, so that later on the hands of the clock can convert these torsional energy and the clock keeps on running. So, that is that is the energy that is stored in actually potential energy in terms of torsional spring. Now, damping is of course the most difficult parameter among the 3, and there are various models of damping like viscous damping, like Coulomb damping, material damping, hysteretic structural damping. I will talk about it when the time will come. So, these are the 3 things that are used in terms of describing the system, the vibrating system: inertia, stiffness and damping. Next we go to the excitation and the response of the system. As I told you that there are 3 things that we have to talk about: the system, the excitation and the response. Excitation and the response of a system are often characterized by some physical variables depending on the application like displacement, velocity, acceleration or stress or noise, etc. Now, which will be used in terms of excitation and which will be used in terms of response actually varies enormously from case to case. I give you a very simple example. Many of you use your cycle or a car for example, and you have the experience of actually going over a bump like this. Okay. Now, if you when you are going over a bump like this, you would see that the as soon as you are crossing the bump, you get a jerking motion, and if you can place an accelerometer on your car, you will see that the car is vibrating for some time and then the vibration is actually coming down. So, you will see something like this kind of a response that is happening in the car. Now, in order to measure that whether your car or your bike etc. is good or not, we actually have a parameter called ride comfort. This ride comfort depends on two things. One is the excitation, that in this case is coming because of the bump, and that is defined in terms of the displacement. Okay? That means you can see what is the bump height here. So, that is the displacement. Okay? So, the force excitation here is coming in terms of displacement. And what is the response? The response is in terms of acceleration of the system, mostly vertical acceleration, there can be other sidewise acceleration. So, in this case the ride comfort case of this thing, we have the system is like an automobile system with its you may say the simplest description of the automobile system is something like a quarter car description of the system. That means the mass of the automobile, at least 1/4 of it, some spring and some damper. So, that is what is our system, and then our excitation is in terms of what you have seen here, that is in terms of the displacement, and our response here in this figure, which is in terms of the acceleration. Now, this thing can vary from case to case. This is just a case where these are the input and the output. There are many other cases where this will change. Okay? For example, if you think of a standard case of a vibration of a tool. Okay? So, there the tool vibration case, the excitation will be in terms of either it will be the acceleration that it will be subjected to, or it can be in terms of the force, that it is the variable force that it is subjected to, and the response will be in terms of the displacement or the velocity. So, thus from case to case this gets changed. Now, what are the ways in which I can control this vibration? Because now we know how to quantify the vibration. The control of the vibration can be either through a passive action, which means it is independent of the resulting vibration response, we call it as an open loop system, or it can be an active action where it is dependent on the resulting vibration, and we will call this as the closed loop system. So, there are these two strategies. In fact, if we put all of them together, all kinds of vibration control that is available today in the world, you will see this broad picture here, that the the basic description of the vibration, as I have just described, source, system to response, that is remaining there, source, system to response, okay, and the excitation is coming here to the source, and then the system is getting excited and you are watching the response of it. Now, to control it, strategy number 1 could be, there are 5 strategies in all that you will have. Strategy number 1 could be that you reduce the excitation at the source itself. Strategy number 2 could be that you do some modification on the system so that it does not get vibrate. The third one could be you put a barrier like that satellite thing I told you, that ultra quiet satellite where the payload and the rocket in between you put a the active Stewart platform. Similarly, you isolate this, that means you do not allow the source to go and excite your system. That is the third strategy. These three are generally passive strategies. Of course, there are some active variations possible in 2 and 3. The fourth strategy is that you actually sense the response and you do something like an additional excitation which cancels the effect of the original excitation. So, they negate each other. Okay? Force and a counter force, they are working together, but in a opposite direction, so that they negate the ultimately the effect of the vibration. So, that is the case of an active control, because in order to determine what will be this additional excitation, you have to know from the response what is your direction of motion, then you have to determine how to give this additional excitation. Finally, some people have very intelligently used the vibration itself in terms of generating energy. So, that is what is called energy conversion, that is what is our fifth step. It is also known as energy harvesting. So, what happens in this case is, as you know, that energy can never be destroyed, it can be transformed. Now, if that be the case, then the energy that is there in mechanical vibration, we know already that some part of it get dissipated due to damping, like in terms of thermal energy or in terms of sound energy. But can we not actually extract it more meaningfully such that we can generate a voltage out of it? So, piezoelectric materials precisely do that. I will show you later on, and that piezoelectric materials precisely can convert these vibration in terms of electrical energy, and then you can keep a kind of a capacitor and then a battery system, so that you can charge batteries out of it. So, that is my fifth strategy of vibration control. So, if we say about it in a nutshell, that first strategy should be always to reduce the excitation at source, second strategy should be that you modify the system, third is that you isolate the vibration, fourth is you measure the response and find out a way to negate the effect of vibration by generating a counter force, and fifth is you harvest the energy and convert the mechanical energy to some useful form of energy. So, this you have to keep in your mind. Talking about the first strategy, we will now talk about the reduction of excitation at the source itself. There are many examples where we can actually, and this is the cheapest one, that if there is a vibration, you should always try to resolve that problem in the root cause of the problem itself, whatever is causing it. For example, if the vibration is happening due to unbalance of inertia forces, okay, so then you can actually use the kind of a strategy to understand that what is causing this unbalancing of the inertia force, and you can try to remove that unbalancing itself. Then you do not have to do any more thing in terms of vibration control. There can be cases where vibration happens because of the flow, we call it as a flow induced vibration. I will give you some of the examples of it, where you will see that the flow induced vibration is taking place. So, in that case also, if you can change the flow characteristics, then you can actually remove the vibration at the source itself. There are cases of parametric excitation, where you can remove the parametric variation, so that this parametric excitation does not take place. There can be cases of some of the examples belonging to these cases only, like reduction of friction or avoiding vortex shredding, etc., to reduce the self excitation of a system. So, the point here is that if you can identify what is causing the vibration, and if it is in your hand that you can modify that characteristics, that should be always your first strategy to control vibration. Some examples I will give you to further elaborate it. Many of you have seen in terms of when you see the aircraft so to say air shows, etc., or if you are close to an airport, you would see that these exhaust coming out of an aircraft is actually generating vortices like this. these vortices create terrific sound. It not only creates problem to the surrounding, but it creates problem to the aircraft itself. This sound actually hits the aircraft. Jet noise is about 1% of the jet energy of an aircraft. Now, how do we control it? Because the root cause we know is because of the exhaust that is coming out, that is actually generating these eddies, as you can see that it is generating these eddies, and these eddies, as long as they are smaller eddies, they are actually of high frequency, but they gradually expand and they become larger eddies, then they become actually low frequency, and that happens away from the jet itself. And these larger eddies are actually large for the jet diameter, and they are at a low frequency, so they do not get attenuated very easily. So, the challenge is that if you can stop the generation of these larger eddies, how we can do it? Well, if you look at this exhaust, instead of having a single exhaust, if you can have this kind of small exhausts, or if you can have a serrated exhaust, then what will happen is that you will not see this expansion of larger eddies, but you will see lot of smaller eddies. And as I have already told you that smaller eddies are having high frequencies, they get attenuated very easily. So, by using this kind of a system, you can actually remove the root cause of vibration, that the smaller eddies from the jet noise will get attenuated very easily and it will not hit the aircraft at all. So, that is one example of reduction of vibration at the source itself. The second example is a case of self-excited vibration. This happens for chatters or friction driven excitations for bridges, for example. So, this is a case of a tower deck bridge, that means the bridge can be opened up or down. Now, if you look at this particular part of the bridge, here it is subjected to enormous amount of counterweight, and if you do not have proper lubrication, then there will be a dry friction in this region, and as a result there will be a friction driven excitation. And if there is a friction driven excitation, as you can see the difference between a viscous friction and a dry friction, that this case the slope is positive, and as a result you are going to have a self excitation in the system. That means there will be a positive work which will be done in the system, and as a result instability will come. So, that is a case of self excitation in the case of this kind of bridge system. The other case is in terms of flow induced vibration, which is also we call it as Karman vortices. In such cases, as has been seen, and I will show you through a small kind of animation. Of this whole thing, that whenever there is a flow at a particular Reynolds number, then if there is a bluff body in front which is facing the flow, okay, what will happen is that there will be formation of eddies in the downstream region, and they come in a very interestingly kind of a in a way that it is anti-symmetric with respect to this line. Okay. So, we call this as a vortex line, one here, another here, another here. So, there is a zigzag line that is formed out of them. Now, this vortex shredding frequency, what it creates is that it creates a kind of a harmonic variation of lift force on this bluff body itself, and as a result this body starts to get excited. So, there is a number called Struhal number that determines this. For example, for a cylinder, the Struhal number is 0.2, and the Struhal number is a function of the vortex shredding frequency f, the cylinder diameter d, which is possibly known to you, free stream velocity is known to you. So, by knowing this 0.2, you should be able to find out the vortex shredding frequency, which will be something like 0.2, in this case 0.2 V over d. So, you know V and you know d, then you should be able to find out what is your vortex shredding frequency. Now, if that frequency is close to the structural frequency of the system, it is definitely going to resonate and it is going to create havoc. So, you need to design your system such that this does not happen. This is just where we are showing that how with respect to the Reynolds number this Strouhal number is varying. As you can see that the Reynolds number, as the flow velocity, free stream velocity increases, the Strouhal velocity changes, the Strouhal number changes, and it changes to a very large extent beyond a certain Reynolds number. So, in these cases the source provides the energy to maintain the vibration, and the sources of vibration could be transient, could be forced excitation, could be self excited, could be parametric excitation. We need to work on each one of these cases to the root cause of it in order to reduce the chances of vibration of the system. This is where we will put an end. In the next lecture, we will talk about other active and passive control strategies. Thank you.